Most buses probably run on diesel engines and are best modeled by the diesel cycle, but hey, you try drawing a car sometime. It's not easy, so we're sticking with a bus. What I really want to know, though, is not what the bus looks like, but rather how its engine works. And we're going to focus on one cylinder within an engine, so we'll model that just as a piston. Really, the Otto cycle is just a complicated piston process. And while I'm talking about it, over here on the right, I'm going to label states and processes on PV and TS plots as we go. So let's start with state 1, which we know has to be a pretty big volume. That piston over there is pretty expanded. So we're going to start at state 1, and what we're going to do is compress the piston until we get to a state 2 on both plots. So let's do that. Okay, we compress the piston, and what we're doing is compressing it isentropically, as you can see from the TS plot. So we didn't change the entropy of the system. We did change the pressure and the temperature and the volume, though. Alright, if we want to model this, well, we need to know something about how that work is associated with other quantities. As usual, when we're modeling complicated cycles, we're going to ignore kinetic and potential effects, so that simplifies our lives a little bit. In this case, well, remember, heat transfer for a reversible process, including processes within the Otto cycle, would be represented by area on a TS plot. There's no area under that vertical line, so that automatically tells us that actually all we need to worry about is the work, and that W over M will just be the difference in internal energies. Okay? So W over M is the difference in specific internal energies of state 2 and state 1 for that process in the Otto cycle. Okay, so we compressed our piston. Now we're going to go to state 3. State 3 is going to be at the same volume, but we're going to transfer some heat. So what we do is we transfer some heat, but we don't change the volume of the piston at all. And as we transfer heat, we do increase the pressure, we do increase the temperature and the entropy. So you can see that state 3 is higher up on the PV plot, higher up and to the right on the TS plot. But we didn't change the volume of the piston cylinder at all. That means that it's a vertical line on the PV plot. No work was done on the piston. Okay, so the expression for that, since we know the work is 0, must just be that actually now it's Q over M that's going to be the difference in specific internal energies. Okay? You may see a pattern here. To get to state 4, we're going to execute an isentropic expansion. And of course, isentropic means that it'll be a vertical line on the TS plot, and we'll go down into the right on the PV plot. Now in that case, we know that work was associated with this. For one thing, the piston moved, but for the other thing, there's area under that curve on the PV plot. And we know that there's no heat transfer once again, because we have a vertical line in going from 0.3 to 0.4 over on the TS plot. So the expression associated with this, exactly as you would assume, would be the difference in specific internal energies for 3 and 4. All right. Final step, well, we have to get back to state 1. This one is, again, going to proceed at constant volume, and what we're going to do is transfer heat away from the piston cylinder now. So we do that, and we get back to state 1. Okay, obviously we change the entropy, the temperature, and the pressure, but not the volume. So the expression for that, using the same logic, is given by Q over M equals the difference in specific internal energy at state 4 and state 1. And just to be clear, the reason all of those relationships at the top are so simple is that for any process you pick, let's pick process 2 to 3 arbitrarily, you're always guaranteed that one of the two processes on a PV or a TS plot is going to be a vertical line. Remember, when you have a vertical line, that automatically means that in the case of a PV plot, the work is 0. In the case of a TS plot, it would mean that the heat transfer is 0. In this case, for process 2 to 3, work is 0. That means we just have to focus on the heat transfer. The only thing it can be related to is the specific internal energy, because we said everything else was ignorable. All right, putting all these expressions together, which works in much the same way as the Rankine cycle, we get an overall thermal efficiency for an Otto cycle that is eta equals all this stuff, which simplifies nicely to 1 minus U4 minus U1 divided by U3 minus U2. So if you can get the specific internal energies for any Otto cycle problem, you're in great shape.